Hey Fizz Kids, Mr. C here, and we're talking about circular motion today, and specifically about vertical circles, because they're a little bit different than horizontal circles. So when we talk about motion in a vertical circle, the reason why it's different is because we have to take into account gravity, and because of that, the forces acting on the ball are actually going to change as we move around the circle. And one note before we really get started into this is that any time that we sort of say what's the positive direction, normally we always say the positive direction is up and the negative direction is down. But whenever we talk about circular motion, that's not necessarily true. Circular motion, the positive direction always points toward the center of the circle. So like this is the positive direction, or this is the positive direction, or this is the positive direction. So it always points toward the center of the circle. The reason why these forces change, and this is kind of weird, so whenever we're looking here and we look at our force of tension, we see, well, we have a force of tension up, and the force of gravity going down. However, when the ball moves up to this point, we have the force of gravity is down, but now the tension is pulling in toward the center. And at this point up here, the force of gravity points down, and the force of tension points toward the center still. And up here, the force of tension points down and the force of gravity points down. So as you can see, as we move around the circle, our net force is going to be the same because we're moving at constant velocity or uniform circular motion. But because that net force is going to be changing what its components are, so like up here down at the bottom, the net force is equal to that force of tension minus gravity. But at the top, the net force is equal to the force of tension plus the force of gravity. So depending on where we are in our circle, the force of tension is going to change. And we're going to look a little bit about how it changes based on where we are in the circle. So at the top of the circle, losing the loop. Yes, at the top of the circle. So in this case, we're just using the normal force, but you could replace the normal force with tension force. It is the same thing. But at the top of the loop, if we look at our forces, the normal force and our force of gravity are pointing in the exact same direction. That means whenever we do our F net equation, that's kind of what this guy is up here. We're just saying that F net is equal to our normal force plus our force of gravity, which has to be equal to our centripetal force, or that mass times centripetal acceleration. We could rearrange that, and we find that the normal force, or the apparent weight, so what you actually feel like, is going to be equal to mv squared over r, or the centripetal force, minus the force of gravity. The weird thing about this, though, is that any time that your normal force is negative, I mean the car, or whatever it is, the car, the ball, the tension force is negative, the normal force, whatever it is that's on the other end, that whether it be a car or a ball on a string, is actually going to fall. And in this case, the car would fall off the track, which would not be good at all. And the reason why is as soon as the normal force is negative, that means it's not really there in this case, and there's nothing kind of holding you up onto the surface, which would not be good. So because of this, we know that there's this critical speed, where if you're going any slower than this speed, you will not have a large enough force to sort of keep you up on top of the curve. And the way that we do this is that critical speed is when Fn is 0. And the reason we say it's 0 is because if it ever went below 0, so that means it's negative, that means our car is falling off the track, and anything above 0 means we're good to go. So 0 is that cutoff point. Whenever we're at 0, like, yeah, we're still going to be on the track, but we're just about to fall off. So when we set our normal force equal to 0, we find that the force of gravity is going to be equal to mv squared over r. Or, if we simplify that, because mass cancels out, we find that v squared over r is equal to gravity. And whenever we solve for v, we know that our critical velocity is going to be the square root of our radius times gravity. So if we're going any slower than that critical velocity, we're basically going to fall out of the air. And that would not be pleasant at all. Or at least I don't think it would be. What's cool is whenever we're at that moment at the critical speed, we're basically going to feel weightless, or like we're in zero gravity. So if you really wanted to, you could hop into your car this week and find a loop-to-loop and see what zero gravity feels like. However, I think you're going to have trouble finding a loop-to-loop large enough for your car, although it would be super cool. We actually had those. I'll have to look into getting one for Lafayette. And like I said earlier, anytime that speed is less than the critical speed, we're going to fall off the track. So like here in this case, we fall off. our track because we don't have the proper speed to basically continue going around a circle like that. So I have a problem now, though. We're going to do an example problem. So I have a bucket of mass 2 kilograms is whirled around in a vertical circle of radius 1 meter. And I want to know at the lowest point of the motion, the tension in the rope supporting the bucket is 25 meters. So I want to know what the speed is of the bucket at the bottom. So if I draw out a free body diagram, I have Fg, and then I have my force of tension. And I'm going to write out my net force because I know my net force has to be equal, because it's uniform circular motion, to mass times my centripetal acceleration, which is also equal to the sum of my forces, or Ft minus Fg. Looking at this, I can say, well, I know that my centripetal acceleration is equal to v squared over r. So I'm going to say mv squared over r has to be equal to Ft minus Fg. Or if I solve for v, I find that my velocity is going to be equal to the square root of my radius times the force of tension minus the force of gravity, all divided by my mass. And I can go ahead and plug in numbers there if you want to, but basically it would just be the square root of my radius, which is 2, times 25 minus, no, sorry, my radius is 1, times 25 minus 2 times 9.8, all divided by my mass, which is 2. If I go ahead and I plug that into my calculator, square root of 25 minus 2. I find that my velocity is 1.6 meters per second, which is pretty fast. I like that. That's a pretty fast swing there. I don't know if I could swing a bucket around in a circle that fast. My next question is, we have a bucket of mass 2 kilograms and it's being whirled around. I don't know why I've done this before. I should know that that's the same question. We want to know how fast must the bucket move at the top of the circle so that the rope does not go slack. The way we're going to do this is we're going to basically find that critical speed. So we know that the rope goes slack as soon as the tension force is negative or goes below 0. So our critical speed is going to be whenever our net force, or not our net force, when our tension force is equal to 0. So in that case, when the tension force is equal to 0, the only force we have acting on our object is the force of gravity. So in this case, we'd say, okay, our net force has to be equal to mass times our centripetal acceleration, which is going to be equal to Fg. From there, I can say, well, I know my centripetal acceleration is v squared over r, which has to be equal to mg. Or, because the m's cancel out, I can solve for v, and I find that my velocity has to be equal to the square root of r times g, which if I go ahead and plug that into my calculator, I find that my critical speed, so I'm going to put a little c here, is going to be the square root of 9.8, which will give me 3.1 meters per second. What this means is that any speed that is less than 3.1 meters per second means that my bucket's basically going to come crashing down on top of me because there is no tension left in that rope. The tension is gone and the bucket's going to just fall down to the ground, and that would not be cool at all. So that is the end of my uniform circular motion problem. If you have any questions, please let me know. I would be happy to answer them, and I look forward to seeing you in class.